Okay. So today, so as I mentioned yesterday, when I answered the question of Dusa, so I talk about Kodaira dimension. Low dimensional. This it's more like a survey. Again, it's a survey talk. This is what Stephen asked me to do. Right. Okay. Of course, I think everybody knows what the holomorphic Kodaira dimension is. But let me a general definition of a Kodaira dimension type of invariant. This is invariant defined on a class of n-dimensional manifold. Takes value in a finite set. Infinity So here, this means the largest integer. All right, so obviously, if n is even,
This is the first word before integer.
Largest integer.
Largest.
Yeah.
Largest.
So, for example, n to 3, this is a 1. Yeah, this is lower floor.
So why do you sit on the class?
On a class, okay. So, well, the original, of course, the class dimension invariant is defined for all and all dimensions. But well, I'd like to have such invariant for all symplectic manifolds, but I'm not able to do that. I have some proposal, but I simply just cannot.
The class to be defined.
Yeah, I cannot define. This notion for all manifolds or smooth symplectic manifolds, but it turns out that somehow okay, you can define this notion in different categories for like a low dimensional manifolds so I give you, I tell you, the story. So some part is quite elementary. Of course, first of all, let me recall the holomorphic Kodaira dimension, so which is
so n is a real dimension.
Yes.
Sorry.
Yeah, and real dimension. So the holomorphic Kodaira dimensions, let me denote it by kappa h. And let me also put this J here. The J, of course, is the complex structure. So this is defined even for complex. Doesn't have to be a projective manifold. Real dimension 2n. This is defined in terms of the Plar genus. So this. Okay, so just this is a classical concept in complex geometry. All right, now I was interested to extend this notion to symplectic manifolds. Okay. Okay, so but let me just postpone that story for a while. So it's just very partial success. Actually, let's try to define, introduce this notion for a more general class of manifold, other class of manifolds, to see whether it's, this concept actually makes sense just beyond just complex geometry. So it turns out you can define.
When you say but different from zero for all L, you mean but different from zero for at least one L.
Yeah, it's non-zero for at least the one L. And that's
For some L.
For some, this is what I said, some L.
And is it obvious that these three are kind of exhausting all the cases?
Oh.
Not totally obvious. I mean, but
So it's either 0 or 1, or it's growing at this polynomial rate, sure.
no, I mean, I think, yeah, I don't think that's obvious.
But this is true.
But it's true. Yeah.
Yeah. Okay. So the story is that actually can be defined for all smooth manifolds. But only up to dimension 3. Okay, so when n is 0, okay. So actually, let's first look at the empty. Well, for empty manifold, it's actually defined the empty set. I assign this minus infinity. And for zero-dimensional manifold, assign kappa to be 0. And then for one-dimensional manifold, I also kappa to be 0 and n equal to 2. There are 3 cases. Okay, so you can define in many ways, but they are all equivalent. So I use actually T to indicate this is a correct dimension for in the topological category. So here we have 3 cases. Infinity 0, 1. So obviously, okay, so we can use just use the Euler class. So this is for a closed,
Oriented.
smooth, oriented. Yeah, that's. But you can extend it to a non-oriented manifold using covering, etc. So but right now let's focus on oriented case. So this is just like S2, T2, and sigma G, G greater than 2. But you can view this in different ways. So you can use like the Euler class the sign of the Euler class, or Yamabe invariant, or the canonical class. The sign, the sign of canonical class of positivity or negativity, the canonical class or vanishing the canonical class. This okay, this is all straightforward. And then
And this definition agrees with the holomorphic one, if it's a complex structure.
that's right. Okay, that's yes. This actually agree with kappa H and two. Yeah,
Or the J,
No matter which.
or the J that you choose.
yeah, no matter what J is, yeah.
Is there an interpretation for a one-dimensional manifold? Is some dimension of something or? Oh, I guess it's.
Well, it's just circle, right?
Yeah, there's a circle.
Oh, why I want to divide zero? Because I want the well, it's e to minus infinity of zero, right?
Yes.
Once a circle is a torus.
Yes, that's right. I want additivity.
I see.
Yeah, additivity, yeah, respect to product, more generally with respect to fiber bundles.
Sure.
So this is so far so straightforward, and then the next in the next dimension, then this notions actually was made by a former student of mine. And he he defined this notion in terms of a Thurston's geometric structures. This okay, geometric structures.
Could you increase a bit the font?
Hmm?
Could you increase a bit the font?
Bigger, right?
Yeah,
Bigger.
yeah,
Okay,
yeah.
yes.
Hard to read it.
Okay, so there are 8 geometries in dimension 3. And so he divided this 8 into 3 classes. And
So the manifolds don't have to be compact or?
well, first I define Kodaira dimension for the geometric structures, just 8 geometries. Then we use the
Sorry.
use the big figures in dimension 3 to extend this to all the assignment to all 3 manifolds. Okay, so I started with just this.
Using the Thurston program.
That's right. Just use exactly. Yeah. That's our so S3 and then the Euclidean geometry, the new geometry, and the solved geometry. Then
For a hapless algebraist, what is H?
oh, the hyperbolic.
Yes.
The upper half.
Dimensional hyperbolic plane. It's a 3-dimensional hyperbolic plane.
I see.
Yeah. So this is well, this is just upper half plane. Like the constant section curvature -1 curvature.
Yeah,
A simply connected model.
yeah.
Different models, disk models, upper half plane model. Yeah.
And then how about E cubed?
Oh, this is Euclidean. Let's just think about R3. R3.
And then how about nil?
Oh, just nilpotent.
The nilpotent.
Yeah, this is solvable.
And then solvable.
Okay, and then For a given a three-dimensional manifold, first of all, you have you can decompose by the prime decomposition. Irreducible pieces, right? Irreducible pieces, and then you further consider toroidal decomposition. For each prime summand. So now M3 is a closed actually here I think the orientation probably is not important. Orientable and connected, let's say. Okay, first of all, I restrict to connected manifolds, but I can easily extend to possibly disconnected n-dimensional manifolds. I'll tell you what we do for manifold, not necessarily connected. And all right, so for such a three manifold, first of all, you have a prime decomposition.
Sorry, you said orientable. Do you mean actually oriented?
It has nothing to do.
If you, that's my question. If you change the orientation, your invariant doesn't change.
Yeah, it's independent orient. Yeah, at least for the three-dimensional manifolds. Because this definition doesn't really use orientation. So you first of all you have the primes, so you decompose into prime summand. Secondly, for each prime summand, consider the toroidal decomposition. I mean, right, bigger prime. So what at the end? So now each piece, so each piece in final decomposition has a geometric structure. So some of the pieces are not closed; they have torus boundaries, toroidal boundaries, but the point is each piece now has a geometric structure. Okay. And then then I just assign the Kodaira dimension now for such a three manifold, and this is minus infinity. If for any by the way, this this is we just consider a decomposition, toroidal decomposition. Okay, and given that decomposition, I assign this number. So this is so each piece has Kodaira dimension. Each geometric piece then it's zero if it's similar to this case. Yeah, not for all L. Okay, so for some piece, it's the geometric piece has Kodaira dimension 0. Okay,
These numbers minus infinity 0, 1, was that by your student? He separated them into these three
yeah,
clusters.
that's right. Yeah, that's what it did.
Geometric structure.
According to the general principle, you should have three values, right? As minus infinity is 0, 1. Just it's of course this is like it's sort of obvious, which one you want to assign 0, assign the value 0. It's like more like Euclidean. Yeah, Euclidean. This is like spherical. It's like a hyperbolic. It's like extending this Yes, standing. So this, if you, in terms of geometry here, okay, actually, see, this is like S2 geometry, this is E2 geometry, and this is hyperbolic 2 geometry in dimension 2. Okay, there are 3 geometry in dimension 2, the A geometry in dimension 3.
You said minus infinity if any for any decomposition. Do you mean for some decomposition? I mean,
What I mean is yes, actually,
because it could-
some, but yes. Well,
What
that's
happens
what
if-
I meant, but it turns out to be
Independent, okay.
Compositions, yeah. That's. Okay, so similar, the story is that for some piece, yes, 0, but all pieces. That's right. And then a similar, I define Kodaira 1, so some piece, that's Kodaira 2. With here, just some piece. Yes, Kodaira division. Okay, then well-defined is has to do with independence of a choice of decomposition. Okay.
Just taking max of each piece. That's just
That's right. That's also taking you can define it. Yeah, the notion of this.
What if you said you could generalize to disconnected? What if I have a 2 torus union a surface of genus 2? You say take the
Take the same principle. Take the max.
let's see.
You have different connected components. Take the max. So it's actually it's not trivial. Just like you need to check this is well defined in a holomorphic category. Okay? You also need to check this is well defined in a topological category. Okay, so. All right.
I'm confused. What's to check? Because the decomposition is sort of unique, or is it?
It's the primary decomposition is unique, but the toroidal one, it's
Not quite unique.
not quite. Yeah. Let's see. and a very nice property of this concept is that if there is a non-zero degree map from M to 3, from M to N, then then the Kodaira dimension M is greater than the Kodaira dimension of N. So it's monotone with respect to non-zero degree maps. Okay, so I have this notion, Kodaira dimension for topological, smooth three manifolds up to dimension, from smooth manifold up to dimension 3. Let me just write down this for what I already said. So for a disconnected manifold. So I define and be the maximum.
Again, yes.
That's maximum of kind of T of MI. So this is a disjoint union of MI. Okay. And then, okay, what happens for higher dimensional manifolds? then this is
There's some sort of additivity with respect to
yes, I will mention that. Yeah, it's already okay. Yes, I want okay. I can mention the additivity here already, but I was planning to mention additivity after I defined the extension to four-dimensional symplectic.
already there's like a bunch of compatibility one would.
Yeah, here already. Yeah, if you talk about compatibility here already, okay. So maybe let's as a fact 3. So then I have this definition for topological manifold after dimension 3. So I just use this to build that extension in all dimension up to dimension 3. So this is additive. So with respect to fiber bundles. Particularly additive with respect to product. That's one reason why I want to assign this number to be 0 for a circle. So that what it means, this is if you have fiber bundle. Have a T. This M. T. So there are non-trivial. Oh, okay. If also it's T is invariant under covering. So that's particular that this is actually this is a special case. Actually, it's just a 0-dimensional fiber. Yeah, particular. So it's here for 3 manifolds. You have non-trivial. You have surface bundle or circle bundle, 2 cases to check. So this is also verified by Wei.
So it's additive basically because when you take A0 of the tensor product, Kodaira dimension is given that A0 of the tensor, the K tensor or whatever, the L tensor product. And so if you have a fiber bundle, locally it's product. So you have, you have the tensor product of, it's a product of 2 tensor products of the base and of the fiber.
Well, for general fiber bundles, for product, what you said, it's also true in the whole complex category, but for holomorphic fiber bundles, it's also just simply it's simply just this the tensor product, or no, I think it's more complex. Yeah, but it's a theorem. This additivity in complex geometry is a theorem. It's right. It's additive. I mean, it's also holds true for not just for fiber bundles, actually more for a fiber. Right?
But actually, in the complex Kähler case, and what we generalize that to we do that to Hamiltonian fibrations, so symplectic fibrations. Then we prove that when it is Hamiltonian actually, which is more general than Kähler and projective. So we proved that the cohomology of the total space splits rationally as a tensor product of the base.
For Hamiltonian,
Hamiltonian
fibration,
and therefore for Kähler and for projective. So this gives an idea that maybe it should work also for non-trivial bundle. It's additivity.
Okay.
It's kind of indication that.
Yeah, I would like to first define, extend this notion to in a symplectic word in object dimension. But maybe, well, I think for maybe can exactly be defined at least for fiber bundles, which are rise of the like this Hamiltonian bundles. So
I said we do that in polytology actually.
Yeah, misremembering. I thought in the holomorphic category there was an inequality, but it wasn't
for fiber bundles. Here, just a fiber bundle
where all the fibers are smooth. Is that? I see. I see.
Like for non-zero degree maps, I have this inequality. This is like related to the inequality, Ithaka inequality, right? This is like a general vibration, non-zero degree map. Yeah, but the covering is a bundle case. I see. The finite covering, unramified covering. Yes, yes. So in higher dimension, there are extensions to geometric manifolds. Just the geometric manifolds, right? This is not all smooth manifolds. Yeah. So along this line, this extension in dimension 3, but restricting to just the special class for that geometry. So they're like in dimension 4, they're like, I think like 27 geometries, many more geometries. You divide it into 4 classes. Four classes, and there you also establish. Well, there's no. He's also this property is also established. The monotonicity with respect to non-zero degree map for such extension to geometry. Okay. So what I really like to talk about is okay, what happens to symplectic manifold? Well, this is actually also old story. This is older story. Starting in the 90s. So actually, it's Cloud. This is after the. So it's Claude LeBron and the Deuce McDuff and Dietmar Salomon all made some initial proposal extending this notion Kodaira dimension to symplectic 4 manifolds. So then the final definitions. So I clarify this concept, and here let me just give you the first of all the definition for so-called the minimal 4 manifolds. Okay. So I explain what the minimal symplectic 4 manifold is, and then how to define this notion for general symplectic. Okay. So for a minimal with canonical class, so this is a invariant second cohomology group. Small values. Right. So it depends on 2 parents. It only depends on the 2 parents. So the class of omega is also degree 2 cohomology class. You cut product 2 degree 2 cohomology class, you get top degree cohomology class, you evaluate on M. I assume it's closed, so that 4 manifolds has orientation, right? It's orientation, so you can evaluate your 4 cohomology class. Right. So here, I start with this 0 here. Okay. So this is the case if both are equal to 0. And 1, if this pairing is 0, but this pairing is positive. 2, if both positive. and minus infinity. You have negativity. One of them is negative. Right. So this
It looks like there's one case missing.
good, very good. Very good. Sharp. Yeah. Yes, that case does not happen for a minimal format, symplectic format of it. Yes, so that's a fact. It's just yeah, the missing case. Yeah. All right, so there's a what that's has to do. This is just saying that it's well defined, right? Again, every time you define this notion, there's an issue of a well definedness. Here, the well definedness is that for a minimal four manifold, this follows from Tao's cyber-Witten theory on symplectic format. So it's a non-trivial, but this even can be defined on a minimal format. So that
Can you write the definition of minimal for me?
I will. Yeah,
I will.
Yeah, yes, yes, I'm saying first, okay, just write down the definition of minimal and explain what this means and extend it to all for manifolds. Okay. In fact, you can define what it means for a smooth form manifold to be minimal. This just means that you don't have any smoothly embedded sphere with self-intersection -1.
It depends what you mean by minimality here, but sometimes, I mean, it's useful to consider CP2 donut at one point to be minimal, because it is the non-trivial S2 bundle over S2. And in this case, in this case, it's useful to consider that as a minimal manifold.
Right. Actually, yeah. In fact, when I study log Calabi-Yau divisors, actually, when I define a minimality in that context, I do have pairs, minimal pairs where the ambient space is CP2 blow at one point. Yeah, so that, in certain situations, yeah, you want to be a little bit flexible, but here, in this context, we consider that to be the manifold to be non-minimal. Okay. So here, you just replace the word smooth by the word symplectic. And okay, So, of course, this is so there's a notion of minimality in for complex surfaces. They're concerned with the existence of a holomorphic, smooth holomorphic rational curves. Of course, this, given it's obviously this from the definition that if the underlying smooth manifold of a symplectic four manifold is minimal, then it's symplectic minimal. Right? But again, Taub's cyber-Witten theory can be used to show that the converse is also true. So this is actually a little observation I made like many years ago. So if the symplectic minimal, then it must be smoothly minimal as well. This is a deep consequence. This is a consequence of a deep theory in right. So here for these class of four manifolds, symplectic four manifold, I have this definition, and then for general symplectic four manifolds, I just reduce to this case. And again, and there is no there again there we need to check well definedness. Oh, this part is due to fact is this okay, actually, here for this to be true, first of all, we have the so-called we have almost uniqueness of the minimal models. What it means is that so if the so the if it's just the middle models. Okay, so actually in certain cases the middle models are not diffeomorphic as smooth form manifolds, but in these cases they all satisfy, all the middle models satisfy the same properties, right? It's like CP2 blow up into 2 points. You can have S2 plus S2 as middle model or CP2 as a middle model, but all the middle model have same Kodaira dimension. And this turns out to be invariant and smooth structure. So namely, given a smooth oriented smooth form manifold, given any symplectic structure on this smooth form manifold, and then you will have the same symplectic Kodaira dimension. This is so although the definition itself depends on the, the existence of symplectic structure, but the value here is independent of this structure. So it bears you the question, it bears the question that can we extend this notion to for oriented four manifolds?
So if you have a diffeomorphism reversing the orientation, what?
Well, then it's not symplectic, right? So it's like it falls out of
You can't have symplectic two omegas with different.
like CP2 bar, right? Yeah, CP2 bar.
I don't know. I'm just I don't know. Yeah. Okay.
Yeah, CP2, you change reverse orientation. There's no.
That's fine. So you place omega with minus omega on. That gives the same orientation. So that's
Yeah. Okay. Wait. Here we're. Okay. Subtlety is we actually. So. CP2 bar. Do you consider CP2 bar as symplectic manifold? Generally, we consider symplectic structure oriented form manifold, right? The symplectic structure induced.
what I mean is you have a four manifold with two different omegas giving opposite orientations. I don't know if such an example exists.
Four-dimensional.
You reverse orientate it's still symplectic. You think this question was studied by Kochik. Yeah, can you find
So you have a four manifold.
Yes, what is it?
And it has two symplectic forms
Yes.
giving opposite
Okay,
orientations.
it's possible.
That's impossible. Is it impossible?
Yeah, yes, yeah, or
It's impossible.
The orientation is given by the
yes,
top.
because if you reverse just omega by minus omega, of course, you get
Yeah,
the
but-
same orientation. Yeah.
But I mean
omega, I omega.
no, I think a T4 you could have this. Right, you dx1 dx2 plus minus dy1 dy. I think there's a conjecture by Kochik saying this kind of class format of very restricted.
Okay.
Yeah, he actually studied.
It's like the signature of the intersection product, maybe is because
So, but you have to have non-zero b plus as well b minus. So CP2 cannot provide such an example.
Right. Yeah.
Okay, this is so I think first of all
Yes, yes, I see, sure. Because on T4 you can see this as a T times T2. And then you reverse all the yeah, omega some omega, and then and then the other is minus omega some omega.
But all of those have the same Kodaira dimension. So
yeah. Okay, so you wonder whether we can remove the orientation. Okay, the oriented diffeomorphism type. Yeah, okay. I didn't think about along that direction.
I think it would be possible, maybe if and only if the manifold is fiber over a surface by a fiber which is symplectic. Yeah.
I think he
I would guess that this.
I think his conjecture maybe it's like such manifold like a surface bundle over surfaces.
okay, so
Yeah, that's it, yes.
okay, so most likely you could drop that word oriented.
Well, but that's actually not true.
Yeah.
Okay. Yes. Okay. Good question. Good. Now, okay, we have at least dimension 4. I have two notions, correct dimension. All right. Yeah. So and this is if a four manifold has both complex structure and a symplectic structure, what happens? Right. Particularly like for a Kähler surface, what happens? Right. So so first of all, it's easy to observe that this give the same value for Kähler surface. Okay, this is Kähler, and then actually. So this it's further shown that that this kappa s is equal to kappa mj. So whenever M has both complex structure and symplectic structures.
So as soon as, if you have the symplectic for symplectic manifold, as soon as you have at least one J which is integrable, then the two notions will agree.
So in particular, this applies to the Kodaira-Thurston manifold. It has a complex structure and a symplectic structure, but it has no scalar structure. So this is considered this like a reasonable extension, right? There is an extension of a holomorphic Kodaira dimensions to from Taylor surfaces to symplectic form manifolds. Then the question, okay, I already raised this question, is can this be extended to kappa T for, oh, let's put our rotation there, already just for safety, already the close smooth format. This is unknown.
Okay, it should, I think it will be difficult.
Difficult, yeah. So you can make some simple extension, like say you can extend it to a virtually symplectic format.
What do you mean?
So it itself is not symplectic, but it has a finite cover which is symplectic.
Okay.
So you see, basically using this additivity with respect to fiber bond. So in fact, this I want to just mention here. Now I have these notions of Kodaira dimension after dimension 4, and it's still it's satisfied additivity holds in most cases. So it's known it is hold in most cases, conjectures always hold. So there's a, so you consider like a mapping tori, circle bundle over free manifold, surface bundle over surface. So there, so this is the additivity is checked in most cases.
And is there any case where it fails or?
No, and there's no fail cases, just the cases which is not known to hold. Yeah. You know. So, all right, so we have this concept, and then then we have 4 classes of symplectic form manifolds. As in the case of complex surfaces, the smaller the value is, the more we know about that class of 4 manifolds. This part. So let me give you some list of families of 4 manifolds. In each case. We know what they are as smooth form manifolds. So they're just the CP2. So I'm just saying M is CP2. Or moreover, as I mentioned yesterday, we know the symplectic structures on such 4 manifolds. So and we know that okay, we actually know the symplectic cone. So this is defined to be the space of classes, symplectic classes. So this is given. So all possible symplectic structure, as all possible cohomology classes of symplectic structure, this is simply given by alpha in H2, where alpha squared is positive, and alpha pairs with E or O E in this set, let's call E of M. E of M is the set of smooth -1 spheres.
I could not read or S2 what minus or sigma
Or S2 bundle.
oh S2 bundle like okay,
Bundle.
Oh. Once again, if you could increase your
Oh, okay.
writing.
So we know which class can be realized by symplectic form, and the cohomologous. So this is under cohomologous forms, symplectic forms. Diffeomorphic. So this is a fact that established by Francis and Dusa, the cohomologous diffeomorphic, and I mean, this is the characterization of symplectic cone. Actually, it is just follows a general characterization of the symplectic cone of all four manifolds with B plus equal to 1. So these are very simple descriptions of which class can be realized by symplectic form. So they all have just B plus equal to 1. So this is true. Or B plus equal to 1 manifold. This description of the symplectic cone. So here, so tomorrow I will say more about the geometry and some geometry aspect of such surfaces for manifolds. But here I want to just mention a open question here is that I also alluded to yesterday. So all these four manifolds are Taylor surfaces. So you can consider, given the complex structure, consider Taylor cone, and there's a notion of a generic Taylor cone for generic complex structure. You know, what's the maximum Taylor cone? What's the maximum Taylor cone? And the question is whether you have equality between the symplectic cone and the generic Taylor cone. This is actually not known for when for most values of L. This is not known whether we have this equality. But for L less than 9, this is true. And for here, for L is less, for this is true for L less than equal to 0 in this case. Okay, this yeah, this is the this is in the I think 1994 paper of Dusa. But when L is greater than 1 in this case, we know this is not true.
So by generic Taylor cone, you mean?
Or you can even take the union of so let generic complex structure.
For generic
Compatible, integrable, compatible. I think it's
Let me actually just use a different version. Let me just take the union of Taylor cone. This is simpler. Okay. So you can call this cohomology Taylor cone. Yes. Any class that is realized by a Taylor form. So this is known to be smaller than symplectic cone if when L is even equal to 1 and G is equal to 1. But as long as you blow up 1 point, you live the root surface.
union over all. Okay, also, so here on the left hand side, when you take the unit, you fix J. J is fixed.
You take unit over OJ.
Okay, all integrable J. Okay, compatible.
So there are still open questions, okay, like particularly for the case of a rational surface.
So I got lost a bit. So you wrote L greater than or equal to 1.
Here in okay. So for S1 over sigma 1, when L is greater than equal to 1, the union of Kähler cone is proper in symplectic cone. It's smaller, generally smaller than the Kähler symplectic cone. But when L is 0, you do have equality. In fact, here you don't have to take a union. Just there's you just take a complex structure coming from a stable bundle, coming from stable rank 2 bundle. Then the Kähler cone, this Kähler cone is equal to symplectic cone. But as long as you blow up 1 point,
It's strictly small.
strictly smaller. And actually, you can determine exactly what this union is. So in the summer, I was one of my students was working on this problem, and then he realized actually there is already a paper in algebra geometry that computing the Sess-Hadley constant in this case that could be used to determine explicitly the union. This in the case of at least 1 point blow up, maybe also for other. So, at least it's a pretty satisfactory picture, right? So we know what the manifolds are, we know what the symplectic structures are, and then in the next case, so which I will probably spend some time on today is okay. This class we call okay. In the minimal case, we call symplectic Calabi-Yau surfaces. Because in this case, since the canonical class can be shown to be a torsion class. In fact, it's at most a 2 torsion. Zero or 2 torsion. There is a conjectural smooth classification. This Kähler or a T2 bundle over T2. So all the minimal symplectic 4 manifold with Kodaira dimension 0 is either a Kähler Calabi-Yau surface or a T2 bundle over T2. So at least there's a conjecture list of 4 manifolds. So what are the Kähler? What are the 4 manifolds here in this category? So they are what's so here you have K3 Brachus. This surface has torsion canonical class topology. And the abelian surface on the hyperelliptic surface, abelian surface, like T4. And here just here we have a smooth classification. By And any T2 bundle over T2 after has a symplectic structure. This is, of course, trivial if the T2 fibers are homologically essential. This is just follows from Thurston's construction. But even when the T2 bundles are holomorphically trivial, the total space still emits symplectic structure. If this is observed by Gygax. He expressed this such a four-dimensional bundle as one bundle over a mapping torus, and they use the construction by Morgan. And Morgan is so to show that the existence of a symplectic structure on any T2 bundle over T2. So it's an infinite. Okay, the list is pretty explicit. So let's just look at this list. Okay. Let's think about their cohomological invariants. So what can you say about the Beatty numbers? See here, all of them B1 bounded by 4. B1 2 sorry, kind of more than 4, right? So actually these two classes of Taylor surfaces also have T2 bound over T2 as their total space. So there are overlaps between these two classes. So B1 less than 4 actually is not certainly surprising because the Taylor case, in the Taylor case, you have a Ricci flat metric. So the first Beatty number is bounded by the real dimension. Because this and B plus is less than 3, and that should be surprising because P plus is 1 plus 2 PG. In the Taylor case, this PG is just 1. This is because the power genus can be either 0 or 1. So PG is the first the power genus. Okay, so these this Beatty number bounds actually hold for any symplectic Calabi surface. This is theorem due to myself and independently Bauer. It's proved a long time ago. And there are some immediate consequences of these Beatty numbers bound. Polar number is not 0. It's greater than not negative. So actually, what the basic bound is this. From this bound, you can first get the first Beatty number bound. So really the basic estimate is this: the bound and the B plus. And then you have the bound on first Beatty number, and then you have the negative the polar number, and then you have the so-called symplectic Noether type inequality holds. So there is a conjecture, the symplectic Noether type inequality that for all four manifolds with non-negative Kodaira dimension, particularly for symplectic four manifolds with general type, meaning the ones with Kodaira dimension equal to 2, there is a symplectic analog, the Noether type inequality. But that is stated actually in terms of the number of Seiberg-Witten basic classes. This inequality involving the number of Seiberg-Witten basic classes. But in this case, the number of this number of Seiberg-Witten basic classes is actually just equal to 1, just the canonical class. And here, what it really means here is this. So it's B plus. So it's an upper bound on B plus, and also involving. Okay, so it's in this form. This related number of basic classes. So this is just saying, okay, for when the canonical class, when the Kodaira dimension of a form, minimum of a four manifold, minimum four manifold is non-negative. Well, actually, the k omega is either 0 or effective, so it can be represented by as symplectic submanifold. And you see what's the map, what's the you look at all the representations of k omega by symplectic submanifold, you allow disconnected representation, and this is just counts the maximal number of representations, and you supposedly, at least in simply connected case, for all these symplectic manifolds with non-negative Kodaira dimension, you should have this bound of B plus in terms of this number. In this number. And in the case of Laplace surface, this is 0. It's k omega. It's 0. It's empty. There's empty. So at least okay, we have we verified this inequality conjecture inequality in the case of Kodaira dimension 0. And right, that's another property is that okay, actually the virtual first Beatty number is also bounded by 4. What's this virtual first Beatty number? This is just a maximal Beatty number of all finite couplings. This is relevant because, okay, in fact, this another consequence of this estimate is this conjecture is really true at the level of homology. Conjecture. So namely the Beatty numbers and the intersection product of a symplectic Laplace surface agree with Beatty numbers intersection product of one of the manifold in the list.
What happens if you have a minimal symplectic Calabi-Yau surface? Do you have any bounds on B minus?
Yes, B minus. Yes, I didn't write that down. Yes, B minus is the 19.
Oh, it is great. So
So I'm saying this actually it's at the level of homology. Okay, so I can draw a table. So you have okay, the B1 line, B2 column, B2 plus column, B minus column, and well, you can write B minus. Maybe heard that, but the order number column and the signature column. Okay. So here, a B1 can be 0. In this case, B2 could be 22, 3, 19, 24, minus 16. And here, this is in the list. So this is a possible cohomology type or homology type of symplectic calabi-Yau. All possible. And then you have 0, 10, 1, 12, minus, this is 9, minus 8, 12, this is Enriquez. So here is a known example. Right? So here on this, okay, but these columns just tell you all the possible Betti numbers. And here on this, the last column tells you actually there's a 1 in the list, realizing that all these types. 4, 3, 2. 4, 6. This is T4.
Something wrong, long B, 3 and 0.
Oh, okay, 3. Yeah. I didn't have this column in my table, but since Mark asked me, I had this column, but I shouldn't just copy it. Yes. Yeah, they're the same. In this case, so 0, 0. Okay. This is a KT. So here, so 2, 2. This is the KT manifold, and then you have 2, 1, 1, 0, 0, and this is the hyperelliptic surface. Okay. Then there. Okay. After this.
Sorry, what's this KT? Okay.
Kodaira system.
Kodaira stuff.
Kodaira still appears in this discussion of Kodaira. Dimensional symplectic format. This is here. So there are other works like studying the fundamental group of such four manifolds. So they want to really promote this.
Sorry, I just want to understand what you've written. So those, if you have a symplectic Calabi-Yau surface, its homology must be in one of those rows.
That's right.
And then there are just examples.
All possible. This is all possible homology type of arbitrary CY. So we know, the homology, cohomology. The question is what about pi 1? Right? There are some progress about this. So this is by. I won't write down the result, but there are attempts to study the results by Reduci and Friedel. So basically, you want to show that their pi 1 is either trivial C2 or a neo Sol type. This is, the pi 1 of this kind of manifolds, just extensions. Z by Z. So it's just very concrete. So you want to show pi 1 of arbitrary SCY is of this form, or you can construct one which with pi 1 is not of this form. Then you got a new one, right? So this is this is still active direction. Okay, I think then I want. So the proof use cyber widget theory. of this theorem. Actually, you use a spin version, the spin version of a Seiberg-Witten theory, because really so first of all, you show this SCY is a spin for a manifold if B plus is greater than 1. No, we want to bound B plus from above, right? So the case B plus equal to 1, we don't need to really consider that case. So assume B plus is greater than 1. Then you first observe that actually the canonical class is trivial, really trivial. So you have a spin structure. Then you can use the pin 2 version. You really have the pin 2 symmetry, extended symmetry. Use the extended symmetry to show the Seiberg-Witten invariant, the canonical Seiberg-Witten invariant is even if B plus is at least 4. And that contradicts to Taub's computations of the Seiberg-Witten invariant of a canonical class of a symplectic 4 manifold with B plus greater than 1. His computation shows that that number is +1 or -1. So particularly cannot be even. So that gives the bound that the B plus has to be less than 3. Yeah. Okay, then think. I just quickly tell you, okay, in the next 2 cases, so kappa S equal to 1. So there are elliptic surfaces. The scalar surfaces with Kodaira dimension equal to 1, and all these Gomp manifold. MG, which has fundamental group any given finite percentage group. So all these Gomp manifolds have Kodaira dimension equal to 1. So we cannot classify it already. Unlike in the complex complex category, you have this, at least you know they're all elliptic fibered, right? There's but here are the question, open question. I think the main question is, Euler number is now negative. That's all known. Here you have this fake CP2. And all these exotic, well, surface general type, right? So more generally, surface general type. Already, you cannot really classify a surface general type, but the main here are the as far as examples concerned, the main interest is about constructing the smallest exotic manifold. So far, the smallest one is holomorphic to 2-point below alpha CP2. So the question is whether you can find such 4 manifold in this category, holomorphic to S2 cross S2 or CP2 below at 1 point. That's all known. Okay, and then here the question is still, the main question is this question still applies here, and moreover you can ask for BMY, and also Okay, here already there is also a related question, the symplectic motor inequality. All number positive, the symplectic motor inequality holds, BMY holds. Okay, this
BMY again, I've lost, what's BMY?
Borg-Molev 比较个1 equal.
Oh, okay.
BMY holds for this symplectic form manifolds Kodaira dimension equal to 2. Actually, there's now is approach by Paul Feehan and Tom Lane. Really, they have a serious approach to the BMY here. Okay, I think I'm almost out of time. I just want to mention that first of all, while you want to extend to higher dimension, we made some attempt in dimension 6, and then we also extended this kappa S 4 manifold to the case of a pair. So this is related to the log Kodaira dimension that you saw yesterday's talk. So here this is defined. Okay, so for this one you use the canonical class. Use the adjoint class. So similarly, so you first prove that every pair can be reduced to a minimal pair in proper sense, and then for minimal pair you define this number in terms of the positivity of the adjoint class. But here it's the success is also partial because here we assume B has no sphere component. Actually, it's a technical assumption that we assume as long as D has no sphere component, then we can really make sense of this relative Kodaira dimension, and it's actually also satisfied a similar property as it's greater than the absolute one. You saw this yesterday. This you could use the log Kodaira dimensions of dominance. Okay, so I just stop here. Yeah, sorry.
So other questions or comments or?
D has a sphere component.
There's no sphere component.
I suppose it does. So then, what is it, a uniqueness kind of issue? What's the problem with that?
There's lots of problems. I'm not saying it cannot be defined. I'm just saying, okay, we didn't try hard enough to deal with the case, because I think in the case when D has sphere, well, actually this okay, what's D? Well, here D is well, initially D is a embedded some manifold, possibly a surface possibly disconnected. We allow D to be disconnected, but you can easily extend to the case where D is configuration. Right, it's configured. You allow a normal crossing, but has no sphere component. So it's still make perfect sense. But when D has a sphere component, I think we need to define it. We need to understand the so-called almost minimal model, like mentioned yesterday, the peeling process. So to say it's about peeling process that I mentioned in yesterday's talk, Polka. So we understand like this construction by Miyanishi described in the book Open Algebraic Surfaces. There are some, I think, interesting. This is an interesting problem, actually extending this to allow the relative notion to allow spherical. In fact, I think it should work because. Maybe yesterday I mentioned I will study I will look at the case where D is just a cycle of the spheres. So cycle of P1. So in fact, in this case, in this particular case, you know, this notion is behave very well. It's just this is the log Calabi-Yau case. It's no problem. There's no problem. Like it's just define the Kodaira dimension in this case when D is a cycle of spheres. But in general, okay, this is interesting. I would say this is. I don't think it cannot be defined. It's much work to do.
Other questions? I have one which is very simple. Yeah. So suppose that you have a minimal Kodaira four-dimensional Kodaira manifold. Then you could use the first K your first Kodaira definition, okay, and then it's the L of the L to the K. Okay.
Oh, the holomorphic.
Yeah, the holomorphic one. But now here it's stopped at 2. So it means that L could not be larger than 2. I mean,
Oh yeah, because here M is a four dimension, right? So there K. I think you know K is at least it's bounded by the K is bounded by N. This is from Riemann-Roch.
K is bounded by L.
Yeah. This follows from Riemann-Roch. Right.
It's bounded by the dimension.
Yeah, by the complex dimension.
Okay.
That can be verified quicker. But why can't it always take an integer value between between 0 and
sorry.
this is if you just see the Riemann-Roch formula, you see the yeah. So here is 2.
Okay, so there is no more question. So let's thank the speaker again. And so we resume at 1:30 with Mark Meckler.